Welcome back, everybody. You may have noticed that we already did this problem, but I want to redo this problem in a different sense using kinetic energy or the idea of the work energy principle. So what the problem states is a smooth 2 kilogram collar is attached to a spring having a stiffness of 3 newtons per meter and an unstretched length of 0.75 meters. If the collar is released from rest at A, determine its acceleration, and we're going to ignore this part of the problem because this problem is pretty straightforward, and then we're going to find the acceleration when h is 1. If you want to see this portion of the problem, then be sure to see the previous video of solving this problem. So if you want to find the normal force, it's pretty straightforward. Just sum the forces in the x direction and you should be able to find it. So the reason why I want to go through this problem again is because you could now apply the concept of energy. Although I wouldn't recommend this method to solve this problem because it is very tedious and very error prone, meaning you can make a lot of errors on the way. But it's also the reason why I want to show it is because it's a different way of thinking about the problem. So the first thing I'm going to do is actually draw the free body diagram, which is mostly the first step of every dynamics problem. And I'm going to choose to draw the free body diagram in the middle of motion, meaning like when this color falls to the bottom from A to C, I'm gonna take this position that's like halfway in between and draw the free body diagram of that position. And the reason why I'm doing that is because we could use this angle and abstract the idea of the free body diagram. So let's also define this angle as theta. So we're going to draw the free body diagram. So I'm going to draw it right here. So the forces acting on this free body diagram is going to be the spring force, which points in that direction. And then there's going to be a weight force, and then there's going to be a normal force going to the left because the collar is on this rod, which restricts its motion in the x direction. And we could define this angle as theta. So I could say this is theta as well by using transversal lines. So from there, what we have to do is define the sum of the forces in the y direction so that we can find the acceleration of the collar when it hits this point. So this is A, and this is C. So let's sum the forces in the y direction. We're going to say up is positive, so sum of the forces in the y equals Fs sine theta minus W, and that equals the mass times acceleration in the y direction. So what we can say, we can rewrite this as Fs sine theta minus mg, which is just the weight of the collar, times the mass of the collar times acceleration in the y direction. Now in the previous example, to find the acceleration, all we did was find the spring force and this what sine theta is in terms of the geometry of the problem, and all we did was divide by m to find the acceleration in the y direction. And that is actually the preferred route when solving this problem. But again, I want to resolve this problem in a different way using the idea of work and energy. So what we learned in our previous videos about energy or work is that we could rewrite acceleration in terms of velocity times the derivative of velocity with respect to position. In this case, we'll use y because we're dealing with the vertical axis. So I'm saying like this is going downward and this is y. So that's what I'm saying there. So that's why we could say the acceleration is just the velocity times the derivative of velocity with respect to position in the y direction. So then we could rewrite this equation again, saying that Fs sine theta minus mg equals m dv dy. I forgot a v, so it should be dv dy. So before we could go forward, we have to actually define Fs and sine theta. So we know that the spring force is actually k times delta x, and delta x is actually how much the spring has stretched from its equilibrium state. So what we can do in this problem is define a right triangle as we did before. We could look at this right triangle with the springs and determine the angle theta and the relationship between its sides of that triangle. So what I'm saying is that the initial state of the spring is right here, and then the final state of the spring is right here. And then we could connect these lines to make a right triangle. So I could say this is L as predefined in the problem, and then this is going to be y, and this is going to be the square root of y squared plus L squared. So to see how much the spring has stretched, which is delta x, all we have to do is take the difference between this side of the triangle and then this side of the triangle. So we could say that delta x is simply y squared plus L squared square rooted minus L. And then we could say as well for theta, so we could say sine of theta equals y over the square root of y squared plus L squared. And since we have those defined, we could plug this into our equation up here, and we could finally take the integral. So if we plug into our equation, this is what we get. So now that we have that, all we have to do is separate these variables in terms of dy and dv, and then take the integral. So before we could take the integral, we have to define our limits of integration. So in our when we set up the equation, the sum of the forces in the y direction, we already specified a direction. So when it comes to the change in position, all we have to do is include this value h. So we could just simply say that the integral for dy is from 0 to h. And for the limits of integration for this side of the equation, we could say this is from 0 to some final velocity. The reason why this is 0 is because it has no velocity in the beginning, because it says the collar starts from rest, as said here. So if you look very closely to this equation, what you're getting right here, this part of the equation just shows the change in potential energy of the spring. And this part of the equation is just a change in potential energy due to gravity. And then this part of the equation is simply the change in kinetic energy. So I just wanted to point that out. That's why we're using this v dv dy. And that's because we get units of energy, and we could see what kind of energy is coming from this problem. So this is just potential energy, this is just gravitational potential energy, and this is just kinetic energy. So before we solve the whole integral, I just want to isolate this part of the equation because this is probably going to be the most difficult to integrate. So I'm just going to isolate this from the rest of the equation and just take the integral of that. So I'm going to look at it from here. So this is going to be, so to take the integral of this, all we have to do is do some u substitution. So we can let u equal y squared plus L squared, and then we take the derivative of u with respect to y, which gives us 2y, and that implies that dy equals du over 2y. So once we have that, we can plug that into our equation. So we can say that kyl divided by the square root of u times dy, which is du over 2y. What we get is the integral of kl over 2 times u to the negative 1/2 du. So I just moved the square root u from the bottom to the top by using a negative exponent, and then I just simplified these constants to kl over 2. So when we take the integral of this, what we get is kl, the square root of u, and then if we plug in back what we said u was, which is y squared plus L squared, that gives us kl, the square root of y squared plus L squared. And then if we do the limits of integration, which is from 0 to h, so this is going to be from 0 to h. So we could actually plug this back in to the equation up above. So I'm going to rewrite this equation in terms of integrals and the solution. So we're going to see 0 to h of ky dy minus kl square root of y squared plus L squared from 0 to h minus 0 to h of mg dy, and this equals the final kinetic energy, which is just that. Again, that comes from this equation right here. So I just separated the integrals from ky and mg and this part right there, which we solved already by this part of the problem. And we simplified this part of the problem, the mv dv, by recognizing that the initial velocity is 0, so it's just the initial kinetic energy. So what we can say is that this is going to be ky squared minus kl square root of y squared plus L squared minus mgy, and this whole thing is going to be evaluated from y equals 0 to y equals h. And we can set this equal to 1/2 mv final squared. So if we plug in the limits of integration, what we could get is so we could simplify this a little bit. So hopefully I didn't lose you so far. You just gotta remember what you're doing in this problem, and as it's stated in the problem, our goal is to find the acceleration of the collar when it reaches c. So since we already have this equation in terms of velocity, or the final velocity squared, we could recognize that the derivative of velocity with respect to time, so we could say d dt of v final, that's simply the acceleration. And another thing to point out is that the derivative of h with respect to time, so d dt of h, that's simply the final velocity. And let me explain that. So when we look at this problem, h is actually this portion, the distance from which the collar falls from this position. So as h changes, the collar is moving along with h. So the distance h changes is the same distance that the collar moves down. So if you find the velocity of the collar, that's like finding the time derivative of h. So you just got to recognize that the derivative of h is just the same thing as the velocity of the collar. And before we move on, because we're going to take the derivative of this equation right here, I want to take the derivative of velocity with respect to time, because some people might forget about the chain rule. So we could say d dt of v final squared, that's going to be 2v final times v final derivative of with respect to time. And as we said earlier, the derivative of v final is just acceleration, so we can actually simplify this saying that this is 2 times the final velocity times the acceleration. Once we understand all that, what we're going to do to this equation right here is divide by m and divide by 1/2 to both sides, so with that we have v final squared, and we could use this idea of derivatives to find the acceleration. So the equation should look something like this. So now to find the acceleration, all we have to do is take the time derivative of velocity, and we could have our equation in terms of acceleration with respect to h. So I'm going to denote the acceleration in the y direction. So we're going to say h dot, which is the same as the time derivative of h, is just going to be equal to the final velocity. So this right here is just the same thing that we said earlier, but I'm using a new notation with the dot. So let's take the time derivative of this. So this is going to be 2km. That's just a constant, and then we're going to take the time derivative of h squared, so we're going to use the chain rule, so that's going to be 2h times h dot. Now we're going to take the derivative of this guy, so this is going to be 2kl over m, and that's just a constant. And now we're going to take the derivative of this square root with respect to time, so the only variable that's changing is h, so we're going to say this is going to be 1/2 times h squared plus l squared minus 1/2. So now we got to do the chain rule, so take the derivative of the inside function. So we're going to say this is going to be 2h, and then we got to take the derivative of h squared, which is another chain rule, so we have to multiply by h dot. So this part might be a little complicated. We just did the chain rule twice because we're taking time derivatives of h. Be careful when you take the derivative of this part of the equation. So we're going to take the time derivative of h over here, so this is simply going to be minus 2g h dot, and then this is just a constant. There's no h or any variable in this part of the equation, so we can say that's that. And as we said earlier, the derivative of velocity squared is simply 2 times the velocity times acceleration, and that's again using the chain rule. So we can say 2vf times acceleration. So knowing that vf equals h dot, we could cancel out the vf's and h dots on each side and have an equation that is set equal to acceleration. So all I'm going to do is divide by 2vf or 2h dot. Okay, I'm so sorry. I found a mistake that I just did. It's a very small error, which is very likely when doing this type of problem. And that's when I took the integral up here, and it messed up a little bit, but it's fine. So I messed up right here, this integral right here. Very simple integral. I forgot to divide by 2. So all this right here is divided by 2. So this is over 2. And then if you do the rest of the problem, there should be another 2 right here. So there's just another factor that I forgot when solving this problem, which I'm sorry about. So if you follow all the way through and you're wondering where that 2 was, it's right here. So after all that, you get your acceleration when you plug in all these values into your calculator equal to negative 9.21 meters per second squared. And that's the same value we got when we saw the problem earlier. So again, it's pretty easy to get lost in the math, so make sure you stay focused on what you're trying to find. Our whole goal of the problem was just to find the acceleration of the collar when it reached point C, or when h equals 1. and I'm going to quickly recap of what we just did in this problem. So the very first thing we did was draw a free body diagram, and our goal was to find the acceleration of the collar once it reaches point C. So the recommended method to solve this problem is just to use this sum of the forces in the y equation right here, and that's because acceleration is already defined by these two forces. So all you have to do is divide by mass and figure out the spring force and the weight, and that's what we did in the previous problem. But I wanted to explore the idea of energy, so we rewrote this equation in terms of this new quantity that we learned earlier, which is acceleration is velocity times the derivative velocity with respect to y, or the change in position. And the change of position is the vertical axis, which we defined as y. So we plugged in this differential in this equation, and we defined the spring force as we did earlier, the change in x, so forth, and we plugged all that stuff in, and then we took the integral. And the first thing we did was write the limits of integration, and since we already defined a direction with these forces, all we had to do is define how far it traveled, which was from 0 to h, and this is going to be from 0 to v final, because we said there's no velocity at the initial state, which is at a. And then we recognize that this is just the spring energy, the change of potential of the spring, and this is also just the change in potential of gravity, and then this equals the change in kinetic energy. So we recognize that this part of the equation is going to be very kind of difficult to solve, so we isolated it and solved it using the u substitution, and then we plugged everything back in and continued with our integration. So this part of the equation is where we use the limits of integration from y equals 0 to h, and I forgot to take the integral of this correctly, so there's a 1/2 right here. And we continue with our integration, plug in values, and what we got was the final kinetic energy equals this stuff right here. And we remembered our goal was to find the acceleration of the collar, so we recognize that the derivative of velocity with respect to time is just acceleration, and we also recognize that the derivative of h, which is basically how the position of the collar changes with respect to the y-axis, that's just the same way of saying how fast the collar is moving, so we could say that the derivative of h is the same as velocity. And then just to point out before we take the derivative of the velocity, is that when we take the derivative of velocity squared, we have to apply the chain rule. So this is actually 2 times velocity with respect to time, which is just 2 times velocity times acceleration. So once we understood those concepts, all we did was take the time derivative of the whole equation, and then all we did was isolate a and recognize that final velocity is the same as the time derivative of h. So when we isolate a, we get this equation right here, and all we have to do, I forgot a 2, all we have to do is plug in the values that were given in the problem, and then at the end of it, you get negative 9.21 meters per second squared, and that is how fast the collar is accelerating once it hits the point C. So again, the purpose of this problem is to have a different perspective when solving this problem. Obviously, if you knew this method, you wouldn't prefer this method over others because you have to deal with a lot of integration and derivatives, which is not preferable because there's a time constraint and you can make a lot of errors, or you're more prone to errors like I was when I took the integral of this very simple integral and forgot a 1/2, which actually changed the problem quite a bit. So this method is just a way to show that you don't really need to know, the idea of physics or the idea of energy. All you need to know is really how to take an integral or solve a differential equation and recognize that acceleration has many different derivatives or differentials with it. So once you recognize that, you could just basically solve this equation. This is the only equation you need, and that's just derived from the sum of the forces equals ma. So if you just understand that concept, you can derive and solve many problems without actually knowing the idea of energy or even the states of energy, like from the initial state and final state, and that's because the math does it for you. So that's just another approach to this problem. Hopefully this helps you. Again, I just want to provide different perspectives or different methods when solving energy problems, because it comes down to this equation: the sum of the forces equals ma, and we could rewrite this in different differentials. So that's just my thing on this. Be sure to watch the previous method of solving this problem, and it will show you why that method is actually easier. In the next video, I'm going to show you how to solve this problem again, but in a completely different way. Well, it's not completely different. We're still using the concepts of energy, but it's more simplified than this method. But overall, the first time when we solve this problem, that is the preferred and easiest method to solve this problem. So the very first method, or the very first video prior to this video about this problem, is the method to use, in my opinion. So with that being said, I'll see you in the next video.